lose anybody on slide 1. All right, so if we start from the very beginning, back when humans didn't know that much about what everything was made of, let's start with water. If we look back far enough, right, we thought this was indivisible. And over time, we progressed into molecules, to atoms, to nuclei, and inside of those nuclei to protons and neutrons, and inside of those protons and neutrons to quarks, where we are today. So I expect everyone's learned up to this part, but perhaps not what's inside of protons and neutrons, depending on where you are in your physics careers. But there are protons or quarks inside of our protons and neutrons. And it's interesting in that there are only two different types of quarks inside of these. So inside of our protons and neutrons, we have up quarks and down quarks, U and D. And then we have our electrons still. They're fundamental particles. We can't break them up into any more bits. But I think it's interesting to think these are the only particles really that make up matter, right? We get all of you, me, the Earth, the stars. These are up quarks, down quarks, and electrons. But I think the really interesting part is this is not the end of it. There are a lot more particles out there, okay? And we've sort of slowly discovered these, not through just looking at what's inside of sort of, or what is inside of atoms and molecules, but also what comes down towards the Earth, for instance, in cosmic rays. And the sort of the particles we started with, up quarks, down quarks, and electrons. These forms were the first generation of our standard model, we call it. And over time, we progressed to also discovering charm and strange quarks. These are in particles like kaons. These are called mesons. And top and bottom quarks. Top quarks aren't in any particles at all. They're only on their own. And then bottom quarks are also in bound states. And then when we start like electrons, we also have muons and taus, which are heavier particles, kind of like electrons, but more massive. And each of these generations gets more massive as you go along. Now, in addition to particles I mentioned, we have this bottom row I haven't addressed yet. And these are our neutrinos. And every lepton has a neutrino partner. And these are in what they call their flavor eigenstates. We have our electron neutrino, our muon neutrino, and our tau neutrino. Now, this whole picture, all of the particles in the matter particles in our standard model, we completed in, I say relatively recently, in 1995. To you, the audience, this probably actually seems like a really long time ago to gauge this, who I'm talking to. But I think it was still relatively recently compared to some of these other particles. And that was discovered by the CDF and D0 experiments at the Tevatron and Fermilab, which is near Chicago. But in addition to all of our particles, we also have our fundamental forces. Okay, so this first one, second one, no problems here, right? They're interestingly with these forces, right? They all vary both in their strength and their range. Now, the gravitational force, which you're all very familiar with, not very strong, but it does have an infinite range, right? So we feel some tiny gravitational force from things in principle across the universe. The electromagnetic force, this was 200 years after the gravitational force when we finally could formalize this. This was Maxwell, who took electricity and magnetism and finally formalized this in Maxwell's equations into the single electromagnetic force. It is a lot stronger than the gravitational force. This is why two opposite charges will be electrically attracted, but not necessarily gravitationally attracted in any significant way in the lab. And it also has infinite range. Now, these other two forces are a lot more recent and a lot more relevant for particle physics. So this is the strong force I have next. It's a strength of 1, very strong. Everything here is relative to the strong force. And it was predicted only in 1971. And it's what's responsible for binding the protons and neutrons together. Those little curly lines I had in there, those are gluons of the strong force. But they're also responsible for binding nuclei together, right? 2 protons in a nuclei in an atom have the same charge, right? They will repel electromagnetically. But the reason they can stick together is because the strong force is much, much stronger when your things are really close together at very small range. Notice this range is on the order of the size of a nucleus. And that only leaves one force left, which is the weak force. Now, the weak force is not as strong as the strong force, but it does act at much smaller range. So it depends what order, how you want to rake these, what order you'd stick them in. Now, the weak force is what's responsible for beta decay. And in this sort of sense, Fermi had described the weak force as a point interaction, means that, or beta decay is a point interaction. He didn't know there were any particles involved, and we'll talk about those particles in a second. But we had these processes of beta decay, of nuclear decay, in the 1930s, but there was quite a long gap between when the weak force itself was discovered in the 1980s, and this was discovered at CERN. So let's go on to how these forces fit into the standard model. So there's a big lag between my slide changes. I'm not sure why. So the fundamental forces, those I just talked about, are mediated by what we call gauge bosons. And those are the particles I've added to the side here. And I indicate which is which. So this is G, that's our gluon mediated. It's the mediator of the strong force. The W and Z bosons are mediators of the weak force. And gamma, the photon, is the mediator of the electromagnetic force. There is no gravity here. And that is a different problem called unification that I will not touch on in this talk. And maybe somebody else will talk about that in a future physics hour, but it's a talk in and of itself. And here, though, with these particles, we're getting quite close to the full standard model as we know it today. But we still need one more thing, and that is the Higgs boson. So the Higgs boson is interesting because we also knew we needed it for quite a long time, or we needed something, right? We had all of these particles we discovered, but the standard model didn't quite work when you wrote it down. So we knew from beta decay and from Fermi's studies of beta decay that weak interactions were really short range. And Fermi had postulated these were basically contact interactions. So there was nothing going on besides two particles just interacting themselves. And then since then, we know they're on order 10 to the negative 18. I'd had that in the slide before. But the problem with that is that the W and Z bosons, if they're massless, they'll have long range interactions, not just contact interaction. They'd have really long range. So a W boson would only allow to affect things kilometers away. And that's not how things work. We knew that wasn't how they worked. But you can't just add a mass to the W and Z bosons, the standard model. It doesn't work that way. It's not something you can do on paper. It breaks basically the standard model, breaks something called gauge invariance, local gauge invariance. I like to think of that as saying like it's like redefining my coordinate system, and that puts me outside of my office, right? It's not what happens. It changes physics by changing something in the equations, right? This is not a very physical scenario. So we can't do that. We can't just add mass to these particles and call it a day, like we, for instance, observed in the 80s. We need a way of giving them mass. It's a bit of a conundrum here. And the way that Peter Higgs postulated we do this is with the Higgs boson. And this was finally discovered in 2012 at the LHC and completed our current picture of the standard model with our 6 quarks, 3 leptons and their neutrinos, the gluon, W bosons, Z boson, photon, and Higgs boson. These are sort of the matter particles in standard model. There are also the antimatter particles. So like an up quark, there's also an anti-up quark. Electron has the positron and things like this. But all of the bosons are their own antiparticles. Often we'll see the standard model like this, but it does leave a little bit out. And this is sort of a wonderful picture. It describes many interactions we see in our experiments, but it's not quite complete, and I'll get to that in a minute. So let's start here, I think, with a timeline of our discoveries, because I think it's interesting to understand some of the history to understand how people approach problems in particle physics. Okay, we had our electron discovery just before the 1900. We slowly moved on protons, neutrons. These are composite particles, so they're not fundamental, right? Made up of quarks. We had muon discoveries in cosmic rays, discovering neutrinos actually before many other particles in nuclear reactor studies. And then there was this age in particle physics between like the mid sort of late 1960s through to the mid 1980s, where a lot of particles were discovered. There's this huge discovery period where we kept seeing new things like, oh yeah, this makes sense. There's all these other particles, or this doesn't make sense. We have to reformulate our entire knowledge of the standard model. And this is where a lot happened. And since then, right, things kind of have slowed down. So we had the top quark in 1995, tau neutrino a little later, and Higgs boson in 2012 to where we are today. And I actually went through at some point and figured out, linked it where these were all discovered. And it's really interesting to understand some of this history, especially when if you're discussing with older people who've been around with them as discovering why we're not doing anything anymore. But there's still a lot to learn. But I think the one important thing to remember is that when we discover a particle, it is just the start of everything, right? So, and I kind of have proof to you here. I looked through archive and looked at the number of papers that were submitted with, I think, top or Higgs in their title or abstract. And when you look at the top work discovery in 1995, so in pink here, you see there's, 100 publications that year, hundreds the next year, and it goes down a little, but it keeps going. And when the LHC turns back on and there's more interesting data, there's a lot more publications. And even today, we're still publishing a huge amount about the top quark. And that's, oh, I can't do math on the fly, 30 years later, right? With the Higgs boson, it's similar. Okay, there's a lot before people thinking about the Higgs boson. Where are you going to find it? What could we do? Let's look here, look there. All these predictions from people, and then discovered in 2012, and then the publications keep going. Right? These are still interesting things. There's still a ton to do after the discovery of a particle. There's something there, but then you have to discover what is its exact mass, what is its spin, what does it interact with, how does it interact with things. All of these are things we need to study about particles before we sort of call the Standard Model complete. And I think then it's interesting to go, okay, well, Standard Model is doing a lot of good things. You haven't discovered anything new yet. What is interesting about particle physics still? And slide change, maybe. There we go. Okay. There's a whole bunch of things we don't know. But I think the two exciting ones to me are, first, what is dark matter? Right. So we have observations, astronomical, cosmological observations about anomalies, right? In galaxy rotation curves. I have that as an example here, and the bending of light around galaxies. So this example here, galaxy rotation curves, I find quite interesting, especially because I make my third year classical mechanics students solve this, or we do this in class. So it's something you can do as an undergraduate to understand why you get this distribution, or that this distribution doesn't make sense. So what this is if you take up all of the mass in a galaxy, and you have a star on the outside and it's rotating around, you'll get some velocity at which that's in a stable orbit. And as you get, as you're inside the galaxy, you're seeing more, there's mass, right? You're seeing more and more mass. So that's the increase here. And as it starts going down, it means you're outside of the galaxy. Outside the galaxy, the mass is just this basically core. It's like the Earth around the sun, right? So you have the same amount of mass, you're just moving farther away, and expect you will go slower around the galaxy, the galactic center. But that's not what you observe, right? So things go faster and faster and faster and faster. And what that's suggesting is that there is more mass that's not accounted for. And that mass is hypothesized to be dark matter because we don't see it with light. So that's a question we can hopefully answer at the LHC or with particle physics. And the other one, slides are driving me insane, is why is there more matter than antimatter in the universe? I have here Earth, right? We know there's an Earth. There is no anti-Earth out there compensating for the amount of matter and antimatter. And I like to think of this in terms of electric charge. So if we start with something that has no charge and you take a positive charge out, you're going to get a negative charge as well because you have to conserve charge, right? And it's kind of like this in the creation of the universe. If you start from nothing and then you create something, you need anti-something to make up for it, to conserve the sort of matter-antimatter imbalance. And that's clearly not the case today. We have ended up in what we call a matter-dominated universe because we are made of matter. Most stars are made of matter. Everything's made of matter. There is some antimatter floating around, but not nearly enough to make up for the balance. And that's, again, a question of we don't understand why in the evolution of the early universe, this imbalance was created. We don't know what happened in the interactions of our particles. Nothing in the Standard Model, no interaction in the Standard Model can account for this. This is another question we try to answer with experimental particle physics. And there's something we say when we talk about questions like this, is the LHC, the Large Hadron Collider, takes us back to the early universe. Now, what that means, or why we care first, maybe, is that dark matter, it exists now. At some point, it was created, probably in the early universe. Matter-antimatter asymmetry, again, it exists today. At the beginning, it didn't, so somewhere along the way, it happened, right? And we don't know where that was. But if we want to study these things, we have to see what interactions could happen in the early universe. And we therefore have to recreate those conditions. So if you go all the way back to the beginning, the universe was really, really hot and high energy. It was really hot. So that's the T, capital T along this axis. The time, little t is time, capital T is temperature. And then we have E in energy. Temperature and energy, effectively the same thing to us. Now, if we want to study what interactions could have happened, for example, this matter-antimatter asymmetry, we have to recreate this. So what we do in our accelerators at the Large Hadron Collider is we take a huge amount of energy into a teeny tiny volume. So the LHC beams are actually very small, right? But we have a huge amount of energy in a tiny area, so very high energy density. And that, with our current technology, takes us back to approximately 10 to the minus 10 seconds, a little earlier. So somewhere just before our dark matter relics, but before everything's stuck in bound states, in mesons, right? So we can create quarks and gluons and all of that, and Higgs bosons. And the hope, right, is that right, the colliders tell us if we go all the way back, we will get, for instance, with the antimatter asymmetry, back to a point where our situation in the standard model is we had equal amounts of matter and antimatter, and we can access these energies to understand what happened in our early universe. And the way we do that is with the Large Hadron Collider. So the Large Hadron Collider is a 27-kilometer ring around 100 meters underground that accelerates and collides protons mostly, but also ions. Right now we are colliding neon, which I think is pretty cool. Every time I look, it's a new ion. Mostly we do lead and proton, but also oxygen, neon, and xenon we've done. But okay, I will talk about protons for most of this talk. Now, inside of this 27-kilometer ring of the Large Hadron Collider, protons are accelerated to a kinetic energy of 6.8 TeV. And this is the center, gives us a center of mass energy of each collision of 13.6 TeV. So when you collide two protons head on, the center of mass energy is 13.6 TeV. And that energy is then available to us to collide to create new particles. And I will explain a bit about that in a minute. Now, we collide at the LHC protons. We collide them in a ring. And there are different colliders throughout history, throughout the last 60 years, 70 years, 80 years, this plot, that were different shapes, right? A lot of times we have linear colliders. So you have one long acceleration. So you have electrons or protons into protons, and they collide, but then you lose your beams. So the nice thing about a circular collider is that your protons are going around and you can keep them. So they can go around and they collide, and then the protons that missed each other can collide again, and they try again and again and again for around, usually in our runs, 14 hours, but up to a full day. And the other thing is that circular colliders, when they accelerate in a circle, are limited by something called synchrotron radiation. So when you accelerate particles in a circle, they radiate, they're accelerating. You're accelerating a charged particle, which means they radiate photons. And this effect is actually lower for higher mass particles, given the magnetic field. And the limitations with the LHC are how strong we can make our magnets. So this means that we can collide protons to higher energies than electrons. So this is why today we're colliding protons, not, for instance, electrons at the LHC. But we have a plan to do that again in the future. Don't know. Okay, so right, at the LHC, we're colliding protons at very, very high energies. And what I mentioned before, the protons, some of them miss and go right through each other. This actually happens quite a lot. This happens most of the time because we can't make the protons collide head on. So what we actually do is make bunches of protons, and we actually put 10 to the 11 protons in each bunch, or approximately order of magnitude. So we're not colliding a proton into a proton. We collide 10 to the 11 protons into 10 to the 11 protons. And we have thousands of bunches of protons around the ring. So they're actually colliding not once and then going around and then again. There's a bunch and then a bunch and a bunch along. So they collide all around the ring. Actually, this is at a rate of 40 megahertz, or every 25 nanoseconds. These slides have a mind of their own. I don't understand. All right. So now inside those proton bunches, it's the protons, right, that collide. But the protons are composite particles. They're not fundamental. They're made up of these quarks and gluons. And it's the partons, these quarks and gluons inside each proton that are colliding. And inside of the protons is really interesting, right? It's not just up and down quarks. The proton is two up quarks and a down quark, and gluons binding this together. But it's not just up and down quarks and gluons inside a proton. You actually, because you have energy in a proton, you have all sorts of gluons that are bringing quark-antiquark pairs in and out of existence. Quark-antiquark because we are maintaining our matter-antimatter symmetry there within the interaction. But you're constantly creating pairs of antiquark quark pairs. And these we call C quarks. So the proton exists in sort of the sea of quark-antiquark pairs and gluons. It's really interesting. It's not just that. Because these are charged particles, quarks, you also get photons. There's also even sometimes photons inside of the proton. Very low probability, but it does exist. And when these partons collide, right, not the protons, but the partons themselves, they undergo inelastic interactions. So not just bouncing off each other, but inelastic and not like car collisions where they smash into each other and become deformed inelastic, but their kinetic energy can be converted into massive new particles. They're actually producing new particles, and that happens around 70% of the time. Sometimes they do just bounce off each other. That's boring. But it's about 70% of the time that something truly inelastic happens. Okay, so when these inelastic collisions happen, new particles are produced. For instance, muons, electrons, photons, or jets. These are quarks and gluons. What they look like in our detector, we call a jet. It's way too complicated for me to get into within this talk. But then the question has, okay, the LHC collided these protons for me. We have these proton interactions. That's all wonderful. We created new particles. Then what? How do I see a muon? I can't just look at it, especially at 25 nanoseconds. My eyes do not have that resolution. Neither do yours. But that's where our particle detectors come in. Okay. So the Atlas detector, and I have a T-Rex here for scale, is right like 40 meters tall, much wider, and contains many, many different, we call them subdetectors, to detect different types of particles. If we start all the way at the inside, we have inner detectors. These are for tracking charged particles. There's a magnetic field. There's a solenoidal magnet, there's down there, that this is inside of. So it bends the tracks of charged particles. So we see their curvature, and we can therefore infer, well, their charge and their mass or their momentum. We can then have calorimeters to measure the energy of all types of like particles like electrons, photons, and hadrons. So anything that's like a quark or a gluon, a charge that has in the detector will be absorbed in these parts of the detector. We get like where they were and what energy they had. And then outside of that, we have this giant, most of the actual volume of the detector is our muon system, we call it. That's both these detectors up top in blue, but also the big wheels at the end. Those are muon detectors. And that's because muons are not very interacting. So when they pass through the inner detector, they're charged like electrons. They'll give us a track. When they pass through the calorimeters, they just maybe give us a tiny bit of energy. Maybe they'll radiate a little bit, but mostly they just pass through. And if we wanted to actually stop them, we would need an absurdly large detector, completely unrealistically big. So all we can do is track where they go. So we have another basically tracking detector on the outside that sees where the muons pass through and helps us know where they were and what their energy or momentum was. So that's how we detect the particles. Now, this is a very large detector, as you see, and you can imagine this does not fit in anybody's lab. This is why we have it at the LHC. But also, it needs a lot of people to understand, characterize, maintain, and operate. So that's where the Atlas collaboration comes in. So the collaboration is a group of people working on the experiment using the Atlas detector. There's about 6,000 people in total on Atlas. That includes engineers and such. But there's basically around 3,000 authors on our papers, 170 different institutions from 40 countries. That's where the institutions are based. The people are from many more countries, and at any given time, around 1,200 students or doctoral students, many more, so undergraduate and master's students. And I just have a map here of the countries showing like the global nature of the collaboration. These are the countries in which we have institutes who are on Atlas. And I forgot to say this earlier. You can, oh no, I have it later. I do have a slide here. So you can, if you want to see the Atlas detector, go to Google Maps and you can tour it on Street View, which is really cool. It's a little old now, 2011, but you can walk around and it doesn't have the best view because you're like right up close to the detector, but it's pretty fun. So now that we have our detector, we know we have our particles are produced. In the inner detector, we can see tracks where the particles were. In our calorimeters, we see these are like the yellow and green blobs, the green ones from our first calorimeter layer, the yellow ones from the second. And then our muons are just straight lines, tracks through. All we do is see where they are, and nothing else makes it that far. So if it makes it that far, we're pretty sure it's a muon. This is an example of a real event display that was from a collision event that happened in 2016 while we were taking data. I forgot, this is actually from one of my analyses. I made this event display. That was pretty fun. Okay. So I just have down below here what these particles, how they look differently in the detector. Right? Muons give us our tracks. Electrons will give us their charge. They'll give us a track and some energy. Photons are not charged. They don't leave a track in our detector. We'll just get some energy. And our quarks and gluons give us a spray of energy. We call it jet. We're probably thinking, okay, there's a lot more particles we talked about in the standard model that you're not mentioning here. Where did they go? And it is true, I did leave a lot of particles out. And that's because we don't observe them directly. Now, we know these particles exist in the standard model, but they're unstable. So they decay far, far faster than we can possibly detect them. Now, what we see inside Atlas are the particles that these particles decay into. So we do not see a Higgs boson traveling through the detector. We don't see a W boson traveling through the detector. What we see is what that Higgs boson decayed into, or what that W decayed into. So we don't ever know if there was actually a Higgs boson. We just know that we saw two particles that look like they came from a Higgs boson. Okay, and this is kind of where that haystack comes in, right? If we see, say sometimes we're looking for, a needle in a haystack, but really in our data collisions, we don't know where a particle came from. We don't know what happened in between because it doesn't give us any indication in the detector. All we know is we see something that looks like it could have come from a Higgs boson. So I think it's more like looking for a piece of hay in a haystack or hoping there's enough pieces of hay to give you a little bump, anomalous, and maybe look like there's some new particle there. Now, when we actually do our collisions, when I said we're colliding them every 25 nanoseconds, it's a bit interesting what we actually go to do with this. This is something that I work on. So I wanted to give you a little information about what's going on here. So we collide these protons in every 10 to the 11 bunches. It's not just a single proton colliding. We get up to 60 collisions in each collision of bunches. Most of these are pretty boring. Just low energy stuff happens. A couple of little particles spray out. No Higgs bosons, nothing interesting. Which is good because we can't record them all if we wanted to. So we choose around 3 kilohertz from our original 40 megahertz of collisions to record of our interesting collisions. And we have to make that decision. Things that are maybe really exciting to study, like a Higgs boson decaying to 2 muons, these can happen as little as once per day. So we're really talking about some low rate processes that we want to study. So we really have to make sure that our 3 kilohertz is actually containing those interesting events. Now, this interesting is subjective, I know, but yeah, this is sort of the huge decision we have to make of what 3,000 events do we decide to keep out of the 30 million that happened every second. And this is part of what I call the double-edged sword of high collision rates, right? If you have 30 megahertz giving you only one Higgs to mu event each day, and I think we'll just collide more protons in each bunch. But if you collide even more protons, you'll have a huge data rate to cope with, right? There won't be 60 protons per collision, there'll be 300. And that takes more sophisticated electronics and detector sort of readout. We have to get more data off of our detector. There are more busy collisions. So that'd be a huge rate of data to cope with. Okay, well, if it's too big, let's just slow it down. And we won't have to take a huge number of collisions down to 3 kilohertz. We can just save them all. But you'd have to reduce it so far that the chance of that Higgs boson to mu event occurring would be like once per year, once per decade, right? This is not realistic. So really, we kind of have to balance the two of these somewhere in the middle, and we always act sort of right on the edge of the most we can possibly cope with in hopes of something interesting happening. And I say it's that Higgs boson event, but also what we're looking for is maybe a dark matter particle that might happen once, twice, three times in the entirety of our data set, and we do not want to miss it. And just to give you an idea of the size of this data, okay, like why do we have to only save a little bit, right? And each collision we have is around 1 to 2 MB when we save it to disk. Those are the interesting ones, or around 1.8 MB I checked this morning. But some of the more boring ones we're throwing away could be a little smaller. So if we go on the conservative side and say, okay, 1 MB per collision, that would fill up I don't even know if my laptop has a terabyte. It's half of that. It would fill up a laptop with a terabyte of storage in a 30th of a second. So, right, this is a huge amount of data. But to compare that to something that I think is truly large, right? Think of compared to the estimate of all of Google's data. This is what, if you Google how much data does Google have, comes up. So it's approximately correct. Say 10 to 20 exabytes. This is huge. And we would fill up like all of the Google data, or create that much in 3.9 days of data taking if we saved every event. So this is completely unrealistic. So we really do have to filter this down by a huge amount to be able to save it. I mean, even if we could save that all, we could put it on disk or on tape somewhere, but we wouldn't be able to analyze it to actually find out what's inside of it because it would take way too long. So that's why we have to do that. Now, there's a whole interesting decision here is, well, now that we know we have to cut down, how do we know what types of events to save? What do we actually save? And there's sort of three categories I think we're in. Things that we know exist and we want to study. I want to study Higgs boson decays, for instance. There's things we've thought of that might exist and we want to search for. It's like my theorist friend thought of a new particle that would decay to this. Let's look for that. And I can make sure we save those types of events if they exist. But then this whole other category of things we haven't yet thought of, we might want to look for in the future. And it's unfortunate, but I think that category on the right there is most of what's out there, right? We can only think of some small fraction. We try to be generic in what we think of, like some particle that could decay to this. But really, most of the things we want to save, I think, are the things we haven't thought of, just because that's where the new physics might be hiding. That's where our dark matter particles might be. So we have to be really careful when designing those event selections that we create a haystack that actually contains all of the hay we want to search for things in. And I just have two examples of events here that we've recorded with the data. And I say candidate events because they're exactly this piece of hay in our haystack, right? We don't know there was a Higgs boson. All we saw is that there are two muons and their mass look at the mass of the particle they came from, it's approximately like the Higgs boson. But there's a lot of background things that could give that as well. Okay? So that's a candidate event for a Higgs boson decaying to two muons. But we also have some, for instance, really cool looking events. I love this event display. This is a super, super high energy spray of particles in one direction and nothing to balance it out. So this is a search for something that would create a dark matter particle recoiling against some standard model activity. It's an interesting event display, but there's nothing beyond the standard model about it, right? There was no discovery of dark matter in 2017. You would have heard about that. So you haven't missed anything, but it's still a really interesting type of search that we do. Okay. I want to talk about a couple or one specific result that I find really interesting, but I have to give you a little background into how to read atlas plots first. So if we want to do, for instance, a measurement of a standard model process, this is something that actually exists. How do we start? Well, first we're going to simulate what goes on, and we're going to determine some event selection requirements. Like there are two electrons, and that will help us select the process we want to study and measure. So there's some selection requirements for those events. We don't take all 3 kilohertz that we record, right? It's some small amount of them. And usually these end up being regions with a lot of signal and low background. And you can see this in the plot I have here. Then we also have to choose some variable that distinguishes between signal and background. So what is on our x-axis? What are we plotting? If we just plot something that signal and background look the same shape as, it's hard to tell what's there. We want something that looks distinctly different, so it's obvious that your signal is there. Then you have to include the simulation of your signal and background. So you want to simulate or somehow otherwise determine all of the different, have mixed up these text boxes somehow. Okay, so the blue arrow should be the bottom. Let's simulate your signal process. So what is the standard model? Or for instance, if it's not a measurement, you want to discover some dark matter, what does your theory predict you should see? You also need to simulate all of the different non-signal processes, all of your backgrounds that contribute to events in your signal region. You will never end up with a completely pure region to do your analyses. There are always going to be other types of events contaminating because we don't know, right, in our collision, if there was the Higgs boson or not. All we know is we see two muons, right? And because we don't have that history, we're never going to be able to make a pure signal region. Then becomes, I think, one of the most important parts, and that is determining the uncertainties on all your predictions. There's always these bands, and those are uncertainties. They include statistical uncertainties, experimental systematic uncertainties. That's like, how well do we actually know how our detector measures electron energy? There's an uncertainty on that. And then also modeling uncertainties or theory uncertainties. We simulate the standard model. That simulation has uncertainties in it. Then, what we do is we get to look at our data. So we don't look at this data right away. We usually run what we call blinded analysis. We don't look at the data until the analysis is final. We don't want to bias ourselves when we're doing these searches or measurements. Okay, we've looked at our data, and then we also generally include at the bottom this handy, we call a ratio plot. And here we divide our background plus signal by our data, and you'll see if there's a disagreement. You'll see like, oh, maybe there's some new physics there, some new particle. But if it's all flat, it tends to be, oh, okay, everything matches. That's kind of boring, but at least we did our job in our measurement. Now, if you look at an actual result, an actual paper, they don't only say these words. Sometimes they'll say these words post-fit in them. Now, in order to determine how much signal, or if there is any signal, if it's a search for some beyond the standard model particle, we run what we call maximum likelihood fits, or that's usually what we'll do. And we'll just float the amount of signal. We'll say, well, let's allow this blue to move up and down and see what is the best fit amount of signal we have in our data. Unfortunately, if it's a search for some new prediction, generally that best fit value is pretty low, around 0, right? Because otherwise you would have heard if we discovered something new. But if it's the standard model so far, again, usually it's right about 1. It's about what the standard model predicts, because we haven't discovered anything new that's anomalous yet. And usually these plots are after that fit is done in a paper. A little side note. Okay, so then what we do is once we have all of our fit and we do this fit, what we're testing is basically the null hypothesis. We want to measure the probability of observing what you see. And is that probability, the probability of observing what we see or more extreme? So is observing that amount of blue, was that, what is the probability of that or even more back or signal events? And what was the probability of that happening? Or what was the probability of seeing that data? And when we do our results, we generally use words like evidence or observation. We only see observation for standard model things so far, but you'll see this in like Higgs boson papers. And we're very conservative in what we call observation of a particle. You see, it's 99.99994% of events. So without that signal, it would have been super unlikely to see a background fluctuation that gave that data. That's what it's saying. It's only 0.000006% of events of times would that background have given that data shape. Okay, so we're very confident when we say observation, right? We're really far away from the p-value of 0.05 you'll often see in other fields. That corresponds to what we call 2 sigma significance. If we get to 3 sigma, 99.7% of the times, this is because there's signal. We'd call that evidence. We're not convinced yet. 5 sigma was our observation value, and that's where that comes from. All right, so there's one analysis I want to talk about, and this is not the normal stuff we do, but looking at the LHC as a photon collider. This is why I mentioned there can be a little bit of photons in the proton earlier. But protons, because they're charged particles, they can radiate photons. And this is also lead ions can do this as well. Keep that in mind because I'm going to use that in a second. Now, if photons are radiated from both beams, so both protons radiate photons, the photons can inelastically interact. And the protons can themselves can actually stay intact when this happens. Sometimes they'll break up, but sometimes they'll stay intact. Now, I think this is completely contrary to our everyday experience, right? Light, the light around me, right? This shines right through each other. We don't see the light colliding in the sky, right? Just think about what would happen if you had a green flashlight and a red flashlight at each other, right? The beams go straight through each other. They don't interact, they don't scatter. That's how classical physics works. That's how electromagnetic, or Maxwell's equations would predict what would happen. But if you're having time to believe this, right, you can try this at home. You can actually do that at home. But the thing is that at the LHC, we're colliding with these photons that are radiated off are such high energy that this is no longer the case. If they come in contact with each other, there is the possibility that they inelastically interact and actually make new particles. So that energy of the photon or two photons is going into massive new particles. So here I have an example where the two photons can create two W bosons. This is a really interesting type of analysis because here it's sort of the opposite of what you normally do. You want to find the interaction where nothing happened, not very much happened. You see the W bosons are what they decay into, but you don't see the proton breakup, all of those tracks. And that's what every single other one of these dots is in all of these tracks. Those are all the other of those 60 on average collisions that happened, all the tracks coming out from that breakup. But we don't see the breakup in these collisions. All you see is the actual hard interaction, those W's, which decay into leptons, electrons, and muons. That's what I have here, but nothing else. So it's sort of a really cool type of analysis that we can do. And then I have a plot here, like I explained, in some signal region with some background processes in all of the colors. And in white here with the blue line, that is the signal prediction. And you can see the data and black dots matched the signal prediction. And this corresponded to an observed significance of this process at 8.4 sigma. This is super, super certain. And we can actually measure what the probability essentially of this happening was. And we did that as well. But even cooler, I think, is that you don't need to create like new particles, W bosons, or leptons or anything like that. You can actually just have photons that scatter and create photons. We call this light by light scattering. This is actually from lead ions because lead ions are more charged than protons. They're actually more likely to radiate photons because they're more highly charged. So you get more photons coming off, so you can create more of this process. So that's why this one comes from a lead ion collision. And here, right, you have the sort of process happens. You have two photons radiated. They don't interact at a point. We don't have photon, 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 photon in a contact interaction. But we have something we call a box diagram because it's literally a box. So that could be like electrons. They interact with some electrons going around a little loop. And then you can have two photons out, but they're different photons, right? They don't have to have the same energies as the incoming photons, the same wavelengths, completely different photons. So I think this is a really cool also event display here because nothing else happens in this event. The lead ions stay intact. They go on their merry way. You just have two photons and that's it. All right. That's some things that we can do with Atlas, but I think I'm being remiss to not talk about what Atlas can't do, right? We don't focus on this. But what happens if all of the hints of all of the beyond the standard model of physics that might explain matter, antimatter, asymmetry, that might explain dark matter, are from particles that don't decay inside of Atlas? They don't give us electrons and muons inside of our detectors. Instead, they just travel on their merry way, all the way, right? We call these perhaps ultra long-lived particles. And these could go for 20 meters, 30 meters, 100 meters before finally decaying into some standard model particles. And the thing is, the LHC could be producing these particles, and we're not looking in the right spot, right? We're looking down here inside of our detector, but we're not looking 100 meters away when they finally decay. So it's important to sort of keep these things in mind when you're doing an analysis in any branch of science, that don't get stuck into what is already possible, what you're doing, but what could you be missing? Okay, so if we think about what we're missing, these ultra long-lived particles, we can think about, okay, how would we actually detect them? And really, realistically, you need a new detector. Nothing with what we built could be detecting them. So here I have an example. CMS is our sort of other detector like Atlas at the LHC. And sort of it's 100 meters or 85 meters underground. And we, instead of trying to fix CMS, it's not possible. It's in a cavern. It's 80 meters underground. We just stick something on the surface of the LHC, like up on the ground, that would have lots and lots of detector around it. That's what these lines are. So when these particles that are traveling decay, we could see that that happens, right? Right now, they could be traveling and decaying just in the air, right? We want to put a detector there. So if they decay, we see the particles they decay into. And we would be able to actually observe if these events were happening and not miss. And the key, this is interesting because the LHC could already be producing it. Even if we don't build this detector, the particles could be there. But the LHC is very expensive to operate. It's very expensive to build. So we want to make sure we take advantage of this as much as we can. All right. So we'll have one more slide about working on Atlas. So what is it like to work in a giant collaboration? And I think it's really neat because you can work on so many different things with so many different people without even changing experiments. So you get bored in one area. It's not like reinventing yourself. You just go, finish up that little project. It's like, oh, I might work in this area now. You get to work with colleagues from all around the world. And often there's a chance to live and work abroad, right? Because the LHC is in Geneva, it's in Switzerland. And you get to work on anything from like designing new detector components, like really hands-on, to organizing outreach events, or as I have in the top here, these are sort of senior management of Atlas and CERN. But they're wearing these t-shirts that I designed as part of, I got like credit towards my participation in the experiment for this. So you get to really do sort of anything you want in the collaboration. And I just want to end with a picture here. This is our actual the detector's underground here, right? Our control room is in that door at the bottom there. Everybody sits in all the computers and makes sure the detector runs right. And this is just a picture of some of us who are working on the Atlas trigger system. So making sure we recorded the right 3 kilohertz of events back in, oh gosh, now 2019. It's been a while. And I'm up there. All right, so that's what I wanted to talk about in 45 minutes, and I can take some questions.
Thank you for your talk. That was amazing. If anyone has any questions, you can put them in the chat or you can raise your hand and turn on your microphone and ask as well.
Also, I love the T-Rex.
Don't be shy. This is your
Yes,
chance. Ask all the questions. Oh, I said
there's a question in the chat from Maria.
Oh.
It says, would a quantum computer be useful in the future to filter out the collision data or even process all of it?
Yeah, so for sure. There are people looking into this for machine learning on quantum computers. It's sort of a little early for that now, but any sort of steps forward